All right. So as I mentioned a minute ago, this is my favorite lecture all semester. So it's a fun thing. Let's say, and I'm sorry we couldn't get the computer lab today. That's a bummer. Didn't expect that. But let's say that two universities offer degree programs. Electrical, or I'm just going to call it engineering, and English. This is chapter 25. Okay. Admission is competitive, and women expect discrimination.
Are you recording?
I am recording. Yes, I'm recording. Okay. So, who's with me? Women, are you with me? Do you expect discrimination? Okay. So, doggone it, where did I put my thing? Here it is. No, it's not.
There's also no, Bennett is the black one. Bennett is black one.
All right, I'm just gonna have to make up the numbers then. Dang it, I can't find my darn thing. All right. So we got men, we got women, we got men, we got women, we got admit, we got deny. Okay. So I really need to find this, dang it. I had it just a minute ago. Because I don't want to mess up my numbers. What could that darn thing be? It's in here. Wrong spot.
Right on us. Oh no, we didn't go to Rexburg. That was way.
All right, well,
We were all thinking.
No, they don't. Oh no, they don't. They don't know that it's a Yeah, no.
here it is, I found it. All right, so we got 35 men were admitted, 45 were denied. We got 20 women were admitted, 40 were denied. Okay? So my question to you all is, since you're all expert statisticians now that you've been in my class, do you think there's discrimination going on?
Yes.
How could we do some sort of math calculation to figure out?
If a higher percentage women was denied, then
We'd probably need to get the totals, right? So we've got 80 men that applied, and we've got 60 women, right? So how could we decide if there was discrimination going on? We could do the percent that were admitted, right? Percent admitted. And so for the men, we've got 35 divided by 80, which works out to be about 43% were admitted, whereas with the women, it was just 33%. So what do you think, women? Is there discrimination going on?
no.
Yeah, looks like it, right? But wasn't that way too easy of a calculation for this class?
Yes.
We can't do anything that easy, right? We got to do it complicated. Okay. So let's do a hypothesis test. Okay. What's the first step?
Write all our numbers.
Find the numbers. Okay, I gave you the numbers. Okay, what's step number 2? Is it categorical or quantitative? Should we vote? Who says it's categorical? 1? Who says it's quantitative? Bunch of people? It was Audrey. Why did you say it was categorical? You said the categories were men and women? Why did you say, was it Lindsay? Did you say quantitative? You didn't vote. You didn't vote. You said quantitative, but because there was numbers there. Well, the funny thing is, Audrey was right, but for the wrong reason.
I was right, so.
Why is this categorical? Admit or deny. Ah. It's not men or women, right? It's admit or deny. Those are the categories. Yeah, she was closer than everybody else. Okay? So these are categories, right? Okay? What's step number 3? 3, find the null and the alternative hypothesis. Okay? Now, I'm going to give this one to you because this one breaks a rule. Okay? Okay, normally a null hypothesis has an equal sign in it, right?
Right.
We're breaking that rule today. This will be the only day we'll break it though. Okay? So I'm going to give this to you. Okay? What we're going to do, here's what you need to remember. So in a nutshell, this is what we're going to call a chi-square test of independence. And so the main things you need to remember is independent versus not independent. But if that's all you write, that's not the right answer. Okay? In this case, we're saying that admission rate is independent of gender. Okay? So this is one that you can actually write a phrase or a sentence. Okay? And so if that's the null hypothesis, what do you think the alternative hypothesis should be?
Admission rate is dependent.
Yeah, we would like to, a lot of you like to say dependent, but the problem is we could have some lurking variables. So we don't want to say it's dependent because it's not like there's something biological that's preventing you from getting admitted, right? Okay, so we're going to say not independent. Admit rate is not independent of gender. Okay? All right, so that's the one I'll give you because this is a new test we're learning today. Okay? Step number 4 is what? What'd you say? Find the test. And the options are a Z or a T or a chi-square. We vote? If you were paying attention, I already gave you the answer, but a lot of you probably didn't hear it. Who thinks it's a Z test? Nobody? Who thinks it's a T test? Nobody? The rest of you were listening. Who thinks it's a chi-square test? Yay! We haven't done that one yet. We're doing that one today. It's going to be a chi-square test of independence. Okay? All right, so here's a few things I want to write on the board. Okay? So, the chi-square test of independence, here's the formulas that you're going to need to remember. The chi-square, it looks like a letter, a kind of an X. It's the Greek letter chi. It's Greek. It's not Chinese. Okay, it's not the chi test. It's the chi-square test. This is the Greek letter chi, and we're squaring it. Okay? Sometimes we write it out as chi-square test, okay? So you lose the point for your name if you call it a chi-square test, okay? On the next quiz, okay? All right, so chi-squared equals the sum of the observed minus the expected squared divided by the expected. Okay, and I'll explain how that works in just a moment.
So that's an OBS.
Observations.
Okay.
OBS for observations. EXP for expected. Okay? Now let's talk about the expected counts. Okay? Expected counts. Okay, now generally speaking, you're going to have a table that looks, well, it could be something like this. Okay? Could be any kind of a table. Okay? So you know that this is row 1, column 1, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, and row 2, column 3. Okay, does that make sense how we're doing this? So I'm just going to give you the formula for this one here, and then you have to, depending on where you are, you're going to change which row or column you're in, okay? So the expected count for this cell equals the row 1 total times the column 1 total divided by the grand total. Okay? So we've already done our column totals. We haven't done our row totals, so we'll do those in just a minute. Also, we have a thing called degrees of freedom. Now, you've also heard of degrees of freedom for the t test. What is your degrees of freedom for your t test?
It's how many you have minus 1.
Right. Now, it's completely different in this one. Your degrees of freedom in this one equals the number of rows minus 1 times the number of columns minus 1. Okay, so it's a completely different formula. Okay, so these are the 3 things you're going to need to remember for this. Okay, all right, so let's go back to our spreadsheet. And I'm sorry that the library was full today. Share, I say. Okay, all right. So we've got the row totals here. We need the column totals as well. Okay, now here's something that you need to be very careful of. I'm gonna do this. In this case, it's not going to matter, but if you have a table like I drew on the board, it will matter and it will cause you grief. Okay, watch this. If I click the auto sum button, it says, is that what you want to add up? And I say, yes, it is. And then I do it again. Is that what you want to add up? Yes, it is. Now watch what happens the 3rd time. Is that what you want to add up? And it adds up the column. Now, in this case, it doesn't matter. But in some cases, it will. Okay? So I'm going to go ahead and I'm going to say, no, I want this. But in this case, it doesn't really matter. Okay? So I've got 140 students in this very small college that applied for these 2 programs. Now, by the way, I probably didn't tell you at the beginning of the class, this is actually, these numbers are completely made up, but this is based on a true story that happened at the University of California at Berkeley. Okay? All right. So I've got my totals. Now, here's what you should do. So I'm going to call this my observed table. Okay? This is what I observed happened. Okay, here's what I'm going to recommend that you do. And I do wish that we could have copied this or done this in the computer lab because you'd have liked it. So what I'm going to do is I'm going to copy this. I'm going to press Control-C to copy, and I'm going to paste it. And this time I'm going to erase all the numbers, and I'm going to call this my expected table. And then I'm going to copy this blank table again, and I'm going to paste it here, and I'm going to call this my observed minus the expected table. Okay? This is a very different test than you're used to. Okay? Now, notice where my box is. I'm in row 1, column 1, right? Okay? So I'm going to follow this formula for the expected counts. Okay? So I want the row 1 total, which is 55, times the column 1 total, which is 80, and I'm going to divide by the grand total, which is 140. Okay? Row 1, column 1, divided by the grand. Okay? Now, Okay, so here's what this is telling me. If the null hypothesis was correct and the admit rate was completely independent of gender, then we would have expected the 31.5 men to be admitted. We got 35. So more men were admitted than we would have expected if gender did not matter. Does that make sense? Okay? All right, we're going to do that for all 4 cells in this case. Now, I'm in row 2, column 1. So I'm going to take the row 2 total, which is 85, times the column 1 total divided by the grand total. Okay? So in this case, if the null hypothesis was correct, the admit rate was independent of gender, I would have expected 48 men to have been denied, only 45 were denied. Okay? All right.
So how do you get to 48 again?
I'm going to do it the same way. We're going to keep following the pattern here. Where am I at? I'm in row 1, column 2. Okay? So I'm going to take the row 1 total times the column 2 total divided by the grand total. Okay? And I'm going to repeat this again for the last cell. I'm in row 2, column 2, right? Row 2 total times column 2 total divided by the grand total. Okay? So this is what my table would look like if the gender was independent of the admission rate. Does that make sense?
Uh-huh.
So I've just done my expected counts table. Okay? Now I'm going to use my chi-square distribution here. The chi-square distribution is, okay, this is the observed minus the expected. Okay, so here's what we're going to do. And parentheses are critical. If you don't use your parentheses, you're going to get the wrong answer. Okay? So the formula is the observed, so I'm going to put equals parenthesis, the observed, I observed 35 men who were admitted, minus the expected, I expected 31.5 to be admitted. I'm going to square that, raise that to the second power, and I'm going to divide by the expected. Okay? And I'm going to do that for all 4 cells. Okay? Yes?
So you use the same expected twice.
You use the same expected value twice. That's correct. Okay? Now I'm in row 2, column 1.
But you didn't do the sum?
I'm going to do I will, but I'm not doing it yet. Okay? So I'm going to do the observed 45 minus the expected 48. I'm going to raise it to the second power, and I'm going to divide by the expected. Okay? Equals the observed, parentheses, 20 women, minus the expected 23.5 to the second power, divided by the expected. And equals the observed, parentheses, observed, minus the expected squared divided by the expected. Okay? All right, now Landon asked me about adding them up. Okay? So at this point, I'm going to add them up. Okay? Basically, I'm going to add up this entire table.
All of it.
The whole table. I'm going to add up the whole table. Okay? In fact, maybe I should change my thing here and make it look like this. Maybe that's why that was confusing. That's probably better. Okay? All right. So, in this case, I'm going to get 1.55. Okay, now I've done the math, but I haven't explained to you about the chi-square distribution. Okay? Now, let me show you a little bit about the chi-square distribution. chi-square distribution. Okay. All right. So here now, before I do that, let me write some more stuff on the board here. Let me stop sharing for a moment. Okay. Now let's talk a little bit about the chi-square distribution. Okay. The chi-square, also called the chi-square distribution. Okay. Number one, the shape changes based on your degrees of freedom. Okay. Number two, it is not symmetric. Okay. Unlike the T and the Z distribution, this one is not symmetric. Okay. Number three, your simple random sample must, your sample must come from a simple random sample. All right, so other rules. Rules when you're doing this test, okay? All counts must be greater than 1. Okay, we don't have that problem. Ours are 25, 35, whatever. They're all greater than 1. And no more than 20% of expected counts are less than 5. Okay, so remember, as far as sample sizes are concerned, remember, if you're using a T or a Z distribution, how big should your sample size be? $30 or bigger, right? If you're doing a proportion test, how big should your sample size be? NPQ should be greater than 10. Do you remember that? Okay. So these are the rules here. All of your counts must be greater than 1. So if you have a 0 in here, it's not going to work. And no more than 20% of your cells can be less than 5. And so here's what I mean by that. Okay. Oh, well. Okay. Let's share our screen here just a second. All right. So let me just say here, okay, let's pretend that when I did the math that I got 4.5 here. Okay. That's greater than 1, so we're okay. But how many cells do I have in my expected table? Got 4 cells, and this cell here is less than 5, right? So 1 divided by 4 is 25%. So this means it's too small. Even though in this case, you know, I've got a bunch of, it's a lot greater than 30, right? But because that cell is 4.5, I should not do this test.
So if you had more cells and only one of them.
If you had more cells, yeah, if I had a bigger table, I could, no more than 20% of the cells could be less than 5. So if I had a table with 20, no more than 4 cells could be less than 5. So if I had 3 cells that were less than 5, I'd still be okay. Okay? All right. So we'll put that back. So that's the sample size. All right. So now let me just show you this here. Okay? Now, when I say that the shape changes based on degrees of freedom, here's what I mean. Okay? For some reason, they use the letter K. I don't know why they use K, but that's your degrees of freedom. Okay? So if you have 1 degree freedom, you're the yellow line. So it's this line here. Okay? If you have 2 degrees of freedom, you're the green line. If you have 3 degrees of freedom, you are the light blue line here. So rather than starting up high, we start low, and it looks like this. Then we've got the dark blue, 4, and 6 is the pink or purple or whatever color that is, and 9 is the red. So you can see that this changes pretty dramatically based on your degrees of freedom, right? Okay. So here's what we mean. Oh, I forgot, there's another rule I forgot to share with you. Okay. I just remembered the other rule. Okay. Another rule here, number 4. Chi-square is always positive. Okay? All right, so typically if you have degrees of freedom more than, well, we don't have, well, let's back up for a second. How many degrees of freedom do we have? Let me share this again. Okay, as I look at my expected table here, how many rows do I have? We've got 2 rows and how many columns? 2 columns. So 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. Okay, so my degrees of freedom in this case is 1. Okay? Now, actually, before I do that, now, just for fun, I'm gonna show you something. If these were independent, let's pretend that I got 35, 45, 20, and 40. Look at my sum. What happened to my sum? My sum is 0. Okay. So if these tables match perfectly, would you say that these are independent? Yes, you would say they're independent, right? There's no difference. There's no difference between these, right? Okay. Now, if these tables are really different, okay, the question is 1.55, is that a big number? And the question is, I'm not sure yet. Okay. But let me draw a picture of what's going on. Okay. Now, with 1 degree of freedom, okay, we know when we looked at this before that this is our chi-square distribution. Okay, this is what it looks like. Okay, if my alpha is 0.05, okay, this is going to be 0. If my alpha is 0.05, okay, this is going to be where I'm going to reject it. Okay, so this over here says do not reject. And then this is my reject region. This is what they refer to as the classical method in the book, I think. Okay? So the question is, where does 1.55 fit? Is it on this side or is it on this side? Okay? And so we need to figure that out. Okay? So here's what we're going to do. Okay? So we need to figure out if 1.55 is on the left or on the right. Okay, so the one thing about the chi-square test that's different from some of the other tests, the chi-square test is always a right tail test. Because if I get a sum of 0, that tells me that my expected and my observed are exactly the same. There's no difference. If my sum is large, then that tells me there's a big difference between what my observed and my expected. Okay? So if I get a big sum, I'm going to reject. And if I get a small sum, I'm going to not reject. Does that make sense?
Wait, say it again. Big sum?
Big sum, reject. Small sum, close to 0, means there's no difference. So you can remember the null hypothesis says there's no difference between your observed and your population. Right. So this would say there's no difference. This would say there's a difference. Okay, so this is the one test that is always going to be a right tail test.
So little sum reject, not reject?
Little sum do not reject, big sum reject. Okay, now let's go to my table here.
Opposite of the P. Because before it's the p-value is low.
Well, we're still going to do the p-value. We're still going to do it. I was just trying to explain it to you. Okay? All right. So let's go back to here. So we're going to follow our steps. So I found my test statistic at step number 4. What's step number 5? Find the p-value. Okay? How many methods are there to find the p-value? There's the table, and there's the computer. The computer is going to be actually very easy. Okay? Let's do the computer first. If you were going to come up with a command for the p-value for the chi-square distribution, what would you call it? Chi-square. Chi-square, and is it a left tail or a right tail test? In our case, it's always going to be the right tail test. Okay? So now it's asking you for x. What do you think x is? It's going to be your sum. 1.55 in this case. Okay? How many degrees of freedom? 1 degree of freedom. Okay? And this is one that you will never ever have to double. It's always going to be a right tail test. Okay? So I got a computer value. We'll do the table. We probably should do the table, right? Okay? So here's how we're going to do the table. Let me pull up my table here. Okay? So we've got a random number table, our normal distribution, our t, and then we've got our chi-square distribution. Okay? Now at the top here, we've got some pictures here. They talk about a right tail test. You're not ever going to do a two-tail test. I don't even think you're going to do a left tail test. So this is the main one you're going to be looking at. This is a right tail test. Okay? We're looking at 1 degree of freedom. Okay? We're looking at this line here. Where does 1.55 fit on this line? So as we go along here, 1.55 is in between those two numbers, right? Okay? So in this case, we're going to say that our p-value is between 0.10 and 0.90, which is a pretty big range, between 10% and 90%. So the computer is going to give you an actual value, but the table you're just going to have to say, well, it's in between these two. Does that make sense? Okay. What's step number 6? Reject or do not reject. Okay. And the answer is my p-value low? What's my alpha? What's my alpha? I didn't tell you, so you assume 0.05, right? Alpha equals 0.05. Is my p-value low? No, so do not reject. Be null. Okay? And step number 7 is write a conclusion in English. Okay? Women expect discrimination. Is discrimination going on?
No.
There is not enough evidence of discrimination against women. Okay? Now here's the funny thing about this. We're out of time. We're going to save this lecture. We're going to continue on with chapter 6. So I'm going to save this, and then we'll talk about this tomorrow. Because didn't it look like there was discrimination going on at the beginning? And now we're saying there's not enough evidence of discrimination. And you remember what Mark Twain said? There are lies, damn lies, and statistics, right? Is this a damn lie?
Yeah, it's a really damn lie.
If you're a woman, it is, right? Okay, we'll talk about this tomorrow. We'll talk about this more. So your quiz on Thursday, maybe we'll push the test back because we're going to cover chapter 6. The quiz on Thursday is on chapter 25 only, and we'll cover chapter 6 next class. Okay? So we'll try to meet in the other place I should have looked when I was there. I don't know. We'll probably push the test off a little bit. Okay. So we'll do chapter 6 on Tuesday. All right. See you all on Thursday. Test is not on Tuesday.